Hi, I'm Wenxiao. This is demo video for Lab 9, Milestone 1. Q-learning with exhaustive and/or random self-play. In this milestone, we implemented a Q-learning agent to solve a maze environment. The maze is an n by m grid with a start position at 0, 0 and a goal position at n-1, m-1. Here we choose 15 by 15. And in our code, here we get we set our the size of our maze. Here, m and n and m is 15 by 15. Around 10% of cells are randomly placed walls, so the agent has to learn how to reach the goal while avoiding invalid moves. Yes, just like we wrote in the codes, the wall ratio is 0.1. Yeah, that means 10% of cells will be wall. And here are the 4 actions: up, down, left, and right. The reward design is positive 100 for reaching the goal, -1 for every move, and -10 for hitting a wall or going off the grid. And here is the code implementation. Here, invalid move, -10, and into the wall, -10. Valid move, just update the state and reach the goal, 100 point, and normal step, -1. The Q-learning parameters are we can see here. That alpha equals 0.1, gamma equals 0.9, and the epsilon greedy policy decays linearly from 0.9 to 0.1 over the first 500 episodes. Yeah, here, alpha, gamma, and decay episodes. To encourage exploration, every fifth episode, the agent performs 3 random actions before following the epsilon greedy policy. We trained the agent for 1,000 episodes and then evaluated it for 100 test episodes with epsilon equals to 0. So after we run the code, the result shows an average of about 28 steps to reach the goal and a success rate of 100%, meaning the agent always finds the correct path. And here is the figure it created. Here is the training reward curve. The blue line shows the total reward per episode, and the orange line is the moving average with a window of 20 episodes. You can see that at the beginning, the rewards are very negative because the agent explores randomly and often hits walls. As learning continues, the reward increases and stabilizes around 0, which indicates that the agent has found an optimal policy. Overall, this experiment demonstrates that Q-learning with epsilon greedy and periodic random exploration can effectively train an agent to navigate a maze environment. That's milestone 1.
Hello, I want to talk about milestone 2, like how we training with historical gameplay data. And in this part, the first things is we need to do the same thing as the milestone one to make it as a data set. So we need to running the milestone one for 500 episodes and reach fewer than 20 steps. The second thing is we need to train our model by the historical data which we run in the milestone one, and we initialize the Q table and use this Q table update for the state and continue training and for another 500 episodes, and then we introduce a custom constraint, and finally we use the evaluation to measure whether our model is performed well. And here's our code. Here we use this function is doing the collection historic data, and we doing this like what we do on the milestone one, and this part we do the pre-train, and here we run the training to read the historical data in this part. Every step we return the rewards to show in the plot, so we can easily to find whether our model learning well or not. And this is the main function. And here we set up the m and n, which is 15 and 15, and the ratio is 0.1, and the learning rate is like here. So this is what we run for this is what's the result. And in this picture, in this part, we show that what we do in the milestone one is the model learn from what he really don't know he don't know anything, and finally it can get it can reward like a very high level, which is 100 in this part. And the next part in this in here it shows us the milestone 2, which is using historical data, and the model learns starting from historical data, and so you can see here it has a very highly total reward beginning, and it's quickly convergence to the baseline. And as you can see here, you only use 500 episodes to make it convergence. And here we can see it also use average step as 26, and it's also 100 successful rate. And this is what we show that the historical learning make our model learn more efficiently and make it learn more quickly. Yeah, that's all.
Okay, this is a demo video for the milestone 3. In this part, we built a DeepQ network agent to solve a maze navigation task. And earlier in milestone 1 and 2, we used the Q table. And now we replaced that with a neural network and added some common DQN tricks like replay buffer, target network updates, and epsilon decay. So let's go quickly over the code at first. As you can see, some interface and it's an environment, and the point is here's class DQN. We use the 3-layer fully connected neural network, each layer with 64 neurons and rerule activation, and outside is the training step. You can see in the training step, the replay buffer size is 10,000 and the batch size is 64. Here, this gives agent enough experience samples for stable learning, and for loss function we used Hoover loss instead of MSE because is less sensitive to outliers and leads to more stable Q-value updates. On the side, you can see the target network is synchronized every 250 steps, which helps reduce the shakes during training. And finally, it's epsilon McGrady policy. It's a decay linearly. It decays linearly from 0.9 to 0.05 over 700 episodes. This controls the balance between exploration and exploitation. And you understand it's the training process. You can see the training curve. Brown line shows the total reward per episode, and the orange line shows it's a 20 episode moving average. At the beginning, you can see the agent performs pretty badly. It bumps into walls a lot, and the rewards are very negative. But after around 500 episodes, the curve flattens and moves up to around 0. This means the agent has learned a good policy and can navigate efficiently. And in the terminal, you can see the results. In our training, we tested the agent for 100 episodes with epsilon set to 0, so it just follows the learning policy. You can see here in the terminal, the average numbers of steps is 28, and the success rate is 100%. We also saved the best checkpoint and reloaded it, and the performance stays as the same, so the policy is stable.